Time for some definitions here in this section. Very long slide here. Don't be intimidated. I'll go through each of these parts one at a time. So definition here, a point x naught, y naught in a region R in the xy plane is an interior point of R. It is in the center of a disk of positive radius that lies entirely in R. So let's draw a picture here for what this might look like. Here might be our R, and so this point here, point P, this is an interior point because we can draw a circle around it that lies entirely inside of R. However, if here is our R, and I were to pick this point here, point Q, any circle that we draw with this point at the center is going to fall at least partially outside of R. So this is an interior. This is interior point, I guess I should say. This is not interior point. Okay, now a point x naught, y naught is a boundary point of R if every disk center at x naught, y naught contains points that lie outside of R and points inside of R. So this run right now, this is not a boundary point, BDY point, boundary point, because this circle does not contain any points outside of R, but this one is a boundary point because it contains points. You know, these points over here lie outside of R. And every single circle centered at this point here is going to contain points that lie outside of R. The interior R is all of R's interior points. The boundary of R is going to be all of R's boundary points. So if I were to draw this picture here, with this is R, the set of the interior R is going to be, you know, that right here. So not counting little dots here, the interior is going to be everything inside of R, and the boundary of R is going to be just the boundary. So this is interior, this is boundary. Our set R is open if it consists entirely of interior points. A set is closed if it contains all of its boundary. These terms here, open and closed, we're trying to generalize the notion of open and closed intervals from one variable function up to two variable functions right now. And so let me get a clean sheet of paper here to have this discussion. So in one variable functions, so let's think about 4, 6, this interval here. So the idea here, okay, so this is the interval. It contains 4 and contains 6. And what's going on here is that 4 and 6, the set of just the points 4 and 6, this is the boundary of the set. This is what separates what's inside the set from what's outside the set. This is the boundary here. The interior is going to be the open interval from 4 to 6. This is the interior. Because the closed interval from 4 to 6 contains its boundary, we say it is closed. But also, because let's talk about the open interval from 4 to 6 now. The open interval from 4 to 6 is the interior of the open interval from 4 to 6. So because the open interval from 4 to 6 consists entirely of interior points, we say it is open. So this is translating open and closed intervals. You know, we know how those work from high school mathematics. We know how those work from high school mathematics. That's translating open and closed interval into the language here of interior points and boundary points here. So now we say a set is open if it consists entirely of interior points. A set is closed if it contains all of its boundary. Okay, we'll do some examples of this in just a moment here. But before we do that, I want to do one more definition slide. So a region of the plane is bounded if it lies inside a disk of finite radius. Otherwise, it is unbounded. So, you know, if this is our R, this is going to be a bounded region. Why? Because I can draw a circle around it. And so you might think, oh, well, anything you can draw a circle around. But the idea here is if your set is this entire first quadrant here, you can't draw a circle around the entire first quadrant. That would be unbounded. So this is bounded. BDD is bounded. This is BDD, unbounded. Okay, let's do, you know what? I'm going to have a bunch of examples. Let me just do one more little picture example here about open and closed, and then we'll do our big example here. So R is open if it consists entirely of interior points. R is closed if it contains all of its boundary. So an open set might look like this. So I'm purposely excluding the boundary here. This is what this is an example of an open set. Whereas we want our set to be closed, we have to include the entire boundary here. So this is, ignore that little smudge there. This is closed, it's including its entire boundary. Note that it's possible for a set to be neither open nor closed. So let me do an example of that. So here I want to have a filled in circle that includes all of the points here, except that this point here is not in our set. So this is not an open set. Why is it not an open set? Does it consist entirely of interior points? No. This is boundary, this is boundary. All of this stuff here is boundary. But is it closed if it contains all of its boundary? Well, that point right here, this point right here is on the boundary R. And so this is neither open nor closed. And of course, we shouldn't be bothered by sets being neither open nor closed. This right here, is a set. This interval in the on the number line is neither open nor closed. It does not. It's closed at this endpoint, open at this endpoint. It does not contain all of its boundary because 6 is on the boundary and does not contain 6. but it does not contain entirely of interior points because 4 is not an interior point. Okay, so that was a lot of definitions. This video is long enough. We'll do some examples in the next video.